We are continuing section 6.4 here. Go ahead and give this one a try if you'd like. Now, the zoo has two other water tanks that are leaking. One tank contains 10 gallons of water and is leaking at a constant rate of 2 gallons per hour. The second tank contains 6 gallons of water and is leaking at a constant rate of 4 gallons per hour. When will the tanks have the same amount of water? So again here, our first step, define our variables. What's changing? I have time and I have gallons of water. Okay, X is going to be my time because the amount of gallons of water depends on the time. So X is number of hours. Y, then, I'm going to have be the gallons in the tank. So for tank 1, okay, it has 10 gallons of water. So the amount of gallons is going to be 10. And is leaking. Leaking means we're going to subtract. So minus 2 gallons per hour means 2 times X because X is our number of hours. For tank 2, the second tank contains 6 gallons of water. So the amount of gallons is going to be 6 and is leaking, so minus, at a constant rate of 4 gallons per hour means times X. Now we have a system of equations here. I have 2 equations, 2 variables. I happen to know what y equals though. I know that y equals 6 minus 4x. So I can substitute that in for y. Again, it doesn't matter which equation we substitute for here. It does not matter because we're going to get the same thing either way. It might just be flipped a little bit. So 6 here minus 4x. And the rest of my equation stays exactly as it's written. Equals 10 minus 2x. I need to get all my variables together on one side, so I'm going to add 4x to go from negative 4 to 0. And whatever I do to one side, I've got to do to both. I have 6 equals 10 plus 2x. I'm going to subtract 10 because now that I have all my variables together on this side, I'm going to move everything else to the other side. 10 minus 10 is how I get to 0. I have negative 4 equals 2x. And to get my x by itself, I'm going to divide by 2. So x equals negative 2 hours. So when will the tanks have the same amount of water? Here, negative 2 hours. And that answer does not make sense when we check there. We can't have negative amounts of hours. We don't know what happened before. All we know is what's happening from now and moving forward. So according to this, never. Okay. Negative 2 hours ago, but that's not an accurate thing. We don't know if it just started leaking. We don't know how much it used to have. We don't know if this leak is the same amount. And so, never. Let's look at the diagram on the top of page 389. Here it says, when a plane travels from west to east across the United States, so from like California to New York, wind acts as tailwind. It increases the plane speed relative to the ground. This happens like when we're walking outside on a really windy day. It feels like we don't have to put as much effort in if the wind's at our back. It seems like it's pushing us along faster. Versus if we're walking into the wind, which is what happens when a plane travels east to west. So from the New York to California. The wind acts as headwinds and it decreases the plane speed relative to the ground. Like when you're walking into wind and you have to try that much harder, it feels like, or when you run laps in Fayed out on the track, when you run your mile. It always seems like one way is a little bit easier than the other, and that's because the wind either helps or hinders. So, a traveler flies from Charlotte, North Carolina to Los Angeles, California. At the same time, another traveler flies from Los Angeles, California to Charlotte. The airspeed of each plane is the same, which means how fast the pilot thinks they're going, like if they had their cruise control on before the wind even impacted them at all. Okay? The ground speeds are shown on page 389. we want to know what is the airspeed, so how fast is the airplane traveling, and what is the wind speed. So the ground speeds here are relative to the ground. So it's the speed that the airplane thinks it's traveling and the wind speed or against the wind. So when we go one direction from west to east, okay, our wind speed is added on to our airspeed, and that equals our ground speed. Again, these are from the diagrams on the top of page 389. And when we travel from east to west, our airspeed minus wind speed equals our ground speed. And that makes sense. It's our speed plus wind because wind is making you go faster, or your speed minus wind because wind is slowing you down, headwind. So when we look here, our ground speed is 550 miles per hour going from LA to Charlotte. So our air speed plus our wind speed, since we're going west to east, equals our ground speed. And our ground speed, again, is 550. Moving the other direction from Charlotte to Los Angeles is our airspeed minus our wind speed, and that equals 495 miles per hour, it tells us here. Okay, and if you forget those formulas, guys, that's okay, because think about what they mean. Something plus another speed is our bigger number, and our airspeed minus the wind is our smaller number. It doesn't matter what our airspeed is. If we add to it, it's always going to be bigger than if we subtract to it. So keep that in mind. Do my equations make sense? Now, if we look here, we can use elimination. Right now we have opposites. Plus W minus W is just 0. So A plus A is 2A. Here I get 1,045. Divide by 2. And our airspeed is going to be 522.5. And since we're talking about our airspeed here, it's in miles per hour. That's how fast the pilot thinks it's going. Okay? If it was the same everything with the plane without the wind, that's how fast the airplane would think it was going. Now, we have to figure out what is that wind speed. So I'm going to take that and plug it in here. Obviously, the pilot's gears and gizmos and things adjust for wind and give them an accurate response there. But if it were to set it at the same amount of gas and things like that, it would always be 522.5 without the wind factored in. Now, to find the wind, we plug that in for A, 522.5 for A, plus W equals 550. We subtract to get the W by itself. We want to know what our wind speed is. And W is going to be 27.5 miles per hour, which seems like just an average Tuesday here. But when we factor in how high the airplanes are, usually winds are a little higher there. So the airplane itself is going 522.5 miles per hour. The wind is 27.5 miles an hour. And going in one direction, it helps it, which makes it seem like from the ground that it's going 550 miles an hour. In the other direction, the wind is slowing it down, and it makes it seem like it's only going 495 miles per hour, which is still pretty quick. Now, you row upstream at a speed of 2 miles per hour. You travel the same distance downstream at a speed of 5 miles per hour. What would be your rowing speed in still water? And what is the speed of the current? So our two things that are changing here is our rowing speed and our current. And in the water, these work the same way as in the air. So our rowing speed is like our air speed, how fast we think that airplane is going. That's going to be where we start both times. When we go upstream, we're against the current. Okay, the current is slowing us down. So we subtract our current, R for rowing speed, C for current, and we get 2 miles per hour upstream. the same distance downstream, and that's 5 miles per hour. So how fast we're rowing and the current gives us 5 miles per hour. Okay, the current is helping us there downstream. Okay, downstream is how the river flows down like a mountain, down a riverbank. So the current goes with that, so we add the current. If not, if you're not sure on that, stop and think. If I start at one speed and I add to it, it's going to be bigger than if I subtract. It doesn't matter what our R is. If we subtract, we get smaller. If we add, we get bigger. So if you get confused on that, just stop and take a second to think about what do these equations mean. Now, since we already have opposites, we can go ahead and add these up. R plus R is 2R. Negative C plus C is 0. And 2 plus 5 is 7. We divide by 2 to get R by itself. And I get 3.5 miles per hour. So you're rowing at 3.5 miles an hour. So if you are doing the same amount of rows with the same amount of force, okay, whether you're going upstream or downstream, that's 3.5 miles per hour. Now to find the current, we take that and plug it into one of our equations. Doesn't matter which one. 3.5 is our R, plus C equals 5. To get C by itself, we subtract. And we get 1.5 miles per hour. So the current is either helping us here at 1.5 miles per hour or hurting us there and slowing us down. But either way, we have both of our values here. Something to keep in mind, guys, here is that when we're doing these, this depends on rates. So if we don't have rates, we need to find them. And remember that distance equals rate times time. So if we divide by t to get our r by itself, distance divided by time is our rate. So if it didn't give us rates here, and here it did, it gave us 2 miles per hour and 5 miles per hour. If it wouldn't have, we'd have had to find those rates. A real quick recap here for section 6.4. Systems of equations can be solved by graphing, substitution, or eliminating a variable. The best method to use depends on the form of the given equations and how precise the solution should be. We can use graphing if we already have a graph or if they're easy to graph. We can use substitution if we already have a variable solved for or it's easy to solve for one. And we use elimination if we already have opposites, can easily get opposites, or if we can't really use either of the other ways very easily. Elimination is kind of our fallback. And that's section 6.4.